welcome back to this series of videos about the Buchwald precatalyst. In the last video, you already know about the 6 generations of Buchwald precatalysts. Today, let's talk about the Buchwald first generation in this second video. Alright, the first generation of Buchwald precatalysts were first published in JACS in 2008. This complex is made of phenethylamine, chlorine, and a phosphine ligand. The author explained that it can be deprotonated in the presence of a base, followed by a C-end reductive elimination to produce an indolent and the active palladium zero catalyst. This process can occur with different types of bases, strong bases like amide bases such as HMDS base at very low temperature, -20 degrees Celsius, alkoxide bases at room temperature, and weak bases like carbonate bases at high temperature. The activation process can be judged by using 31-phosphor NMR or calorimetric analysis. Now, let's take a look at how it was synthesized back in 2008. So, the process to synthesize this palladium complex involves 3 main steps. The first step consists the formation of the intermediate complex via the reaction of diacetonitride palladium chloride and tetramethyl ethylenediamine in acetonitride at room temperature. The second step is a methylation of the palladium complex via the reaction between methyllithium and the previous palladium complex in methylturbidiol ether at 0 degrees Celsius. The third step is the coordination of the ligand, the formation of palladium G1 via the reaction of ligand and 2,2-chlorophenylethylamine with the palladium complex in methylturbidiol ether at 55 degrees Celsius. In this paper, the author successfully prepared 3 precatalysts X-phos, S-phos, and Rufus palladium G1 with excellent use. Each step in the process achieved use over 85%. And the best part is they didn't need a glove box. They just used recrystallization for purification, which resulted in air and moisture stable complex. But it involved the handling of organometallic intermediate. Nowadays, besides S-phos, X-phos, Rufus palladium G1, we can have TPU X-phos and Bradphos palladium G1 commercially available, and you can find them in the Merck catalogs. So, let's see their application. In 2008, Buchwald's group demonstrated the use of the first generation of palladium precatalyst in C-N cross-coupling reaction of electron diffusion aniline with unactivated aryl chloride, achieving excellent use with a weak base like potassium carbonate. Electron deficient anilines are usually tough to work with in C-N cross-coupling reactions due to their low nuclear fission, but these precatalysts can handle the oxidative addition with aryl chloride. The reaction time was significantly reduced from 1 hour to just 10 minutes when using a stronger base like sodium terbutoxide, even with very low catalyst loadings, less than 1% of palladium, in this case 0.11%. It's common practice to add the ligand with the precatalyst, and I usually do this in my Buchwald reactions. As you can see here, the reaction between morpholine and aryl chloride can be done at room temperature using S-phos palladium G1 and sodium teramoxide, or at -10 degrees Celsius with Rufus palladium G1 and HMDS. Let's talk about the application of CN cross-coupling with palladium G1 in synthesizing natural products. In order to access to epi-indolactam, Bersanti and co-workers carry out an intramolecular NR relation to give anion membranes. The cyclization step was successfully accomplished in 86% yield using exhaust palladium G1 and sodium taubutoxide at 178 degrees Celsius in a microwave reactor. Personally, I love using microwave reactor for Buchwald cross-coupling reactions because it speeds up the process and the reaction can be heated at higher temperature. So, to sum up our discussion about Buchwald G1 precatalysts, which were mainly used for making CN bonds, however, its activation in the presence of a weak base is low and only occur at elevated temperature. This limitation makes it unsuitable for Suzuki reaction involving unstable boronic acids like polyfluorophenyl or 2-furan or 2-thiophene boric acid with other aryl or heteroaryl halides, as these boronic acids quickly deboronate under basis conditions. So the reaction could only occur if the generation of the catalytically active palladium zero species is weakly under my condition under which the deboronation of the boronic acid is significantly slowed down. The solution for this problem is the creation of the new generation of palladium precatalysts by Bergman groups. In the next video, we will take a closer look at how these precatalysts are designed and why they represent a major improvement in catalytic performance. Thank you for watching. Have a nice day. Bye.